Data preprocessing is an important stage in preparing a dataset for the application of various machine learning methods. The better we prepare the data, the more accurate and reliable the analysis results will be in the end. So here's what we're going to do today. First, we'll talk about our goals, what we actually want to achieve with data preprocessing and why it's worth spending time on. Then we'll move on to the introduction part, where we'll see what data preprocessing actually is and go through its main steps. Next, we'll look at how to detect duplicates, those repeated rows and columns that can appear in your dataset and confuse your model. After that comes missing values. Sometimes our data just isn't complete, and we'll see a few simple ways to handle this problem. Then we'll move on to outliers, those unusual data points that can affect your results if you ignore them. We'll also talk about noisy features, columns that don't really help and might even hurt our model's performance. Once the data is clean, we'll go over how to encode features, basically how to turn categories into numbers, so the machine learning algorithm can understand them. We'll also take a look at polynomial features, how we can create new features from the existing ones to capture more complex relationships. And before we finish, we'll cover feature scaling, making sure all our features are on a similar scale so the model doesn't get biased toward larger values. Finally, we'll wrap everything up with a short conclusion and connect all these steps into one clear workflow. Let's talk about our goals. We should learn to make sense of why data preprocessing is necessary. Think of data preprocessing as operations on a feature matrix with rows as objects and columns as features. Use the pandas and scikit-learn libraries for data preprocessing. Understand the connection between the mathematical, graphical, and programmatic descriptions of preprocessing methods. So, what exactly is data preprocessing? When we start working with raw data, it's usually far from perfect. It might be incomplete, inconsistent, or just simply noisy. Preprocessing is the step where we turn that messy data into something structured and ready for analysis. In practice, this means a few key things. First, we clean the data, removing duplicates, fixing missing values, and dealing with outliers. Then we reduce noise and get rid of redundant information. And finally, we transform the data by encoding categorical features, scaling numerical ones, or creating new features through feature engineering. The main goal is simple: to prepare high-quality feature matrices that make machine learning models work effectively and produce meaningful results. Let's go over the main steps of data preprocessing and start with duplicate detection. A duplicate is an exact or nearly identical copy of a data sample that appears more than once in a dataset. Duplicates don't add any new information and can mess up our analysis or confuse our model. Getting rid of them helps keep the data clean and the results more accurate. But if you do find duplicates, it might be a good idea to understand why duplicates appear. Sometimes they result from data collection errors, but in other cases, they might actually contain useful information. Here's an example of how to handle duplicates in Python. First, we create a simple dataset with a duplicate. The duplicated function returns a boolean mask showing which rows are duplicates of previous ones. The drop duplicates function removes those duplicate rows from the dataset. In our case, this duplicate is Bob. In addition to rows, that is samples, columns can also be duplicates, meaning repeated features. A feature duplicate is a feature, that is column, that contains the same values as another feature in the dataset. Duplicate features add no value and can confuse the model or inflate the importance of repeated signals. In Python, we can handle duplicate features the same way as duplicate rows, by simply transposing the dataset so that rows become columns and vice versa. In this example, we created a duplicate feature, detected it using the duplicated function applied to the transposed dataset, and removed it with drop duplicates. A special kind of duplicates are near duplicates. These are data items, samples or features, that are not exactly identical, but are very similar to each other, often differing by only minor variations or noise. Near duplicates can appear when data is collected from slightly different sources, or when the same measurement is recorded with minor rounding differences. For example, imagine we have a collection of web pages with product descriptions. Some of them are almost identical, except for small differences in formatting or a few words. Or think of an image dataset where several photos show the same object but were taken from slightly different angles or under different lighting conditions. Near duplicates can make our dataset redundant and may even mislead the model if not handled properly. One common way to detect near duplicates is by checking correlations between features. Highly correlated columns often indicate that the data carries almost the same information. Let's recall how the linear correlation coefficient, or Pearson correlation, is calculated. Suppose we have 3 points with these x and y coordinates. The correlation coefficient helps us understand how strongly and in what direction the variables x and y are related, whether an increase in one tends to come with an increase or a decrease in the other. The correlation coefficient is the covariance normalized by the product of the standard deviations. Let's recall what that actually means. The covariance of two variables is the average of the product of their deviations from their respective means. It shows how the variables change together. It's the combination of these two differences, as we'll see in a moment, that determines the sign of the entire correlation coefficient. The standard deviation is a measure of how much the values of a variable deviate on average from its mean. In other words, it shows how spread out the data is. The standard deviations don't affect the sign of the coefficient. They normalize it, meaning they simply ensure that the value of the correlation coefficient stays within the range from -1 to +1. As we can see, the factor of 1 over n in numerator and denominator cancels out, so the final formula takes the following form. Let's take a look at how the correlation coefficient is calculated using a simple example. Let's find the mean values for x and y. Then we'll calculate their standard deviations. We can see that x has a larger spread than y. Now let's calculate the correlation coefficient by plugging the mean and standard deviation values into the formula. In the numerator, we have the sum of 3 products. The first product corresponds to the first point, the second to the second point and the third to the third point. In the denominator, we have the product of standard deviations. After calculating the products, summing them up and dividing by the denominator, we get a correlation coefficient of about 0.99. That means there is a very strong positive linear relationship between x and y. As x increases, y increases almost proportionally. And as we know, the correlation coefficient can never be greater than 1. If we look more closely at the calculations, we can see that the coefficient turned out positive because the first and the third products were greater than 0. The first product is positive because x1 is below the mean, and y1 is also below its mean, and the product of two negative numbers is positive. The third product is positive because both x3 and y3 are above their means. The y2 coordinate equals the mean, so the entire second product is 0. So, the positions of the points relative to their mean values determine the signs of the products in the numerator, and as a result the sign of the covariance and the entire correlation coefficient. Let's now look at another example. Compared to the previous one, the red point has moved up, the blue one has moved down, and the green one stayed in the same place. The mean and standard deviations remain unchanged. By doing the same calculations as before, we get a correlation coefficient of minus 0.99. This means there is a very strong negative linear relationship between x and y. As x increases, y decreases almost proportionally. If we look closely at the numerator again, we can see that in this case the first and the third products are negative. This happened because the signs of the differences are opposite to each other. For example, x1 is below the mean, while y1 is above it. As a result, the sum of these negative terms gives us a negative covariance and consequently a negative correlation coefficient. In the third example, let's move the red point down to almost the same level as the blue one. The resultant correlation coefficient is close to 0, which means there is no clear linear relationship between x and y. Changes in one variable do not consistently correspond to changes in the other. This happened because the positive first and second products compensated the negative third one. It's important to understand that what we've just discussed is the Pearson correlation coefficient, or linear correlation. It measures how well the relationship between two variables can be described with a straight line. But sometimes the relationship is nonlinear, for example, when one variable grows exponentially or follows the curve. And in those cases, Pearson correlation might be close to 0, even though the variables are clearly related. Now let's look at something called Anscombe's quartet, a famous example that shows why visualizing data is so important. Anscombe's quartet is a set of 4 different datasets that all have almost identical statistical properties. They share the same mean, variance, correlation, and even the same linear regression line. But when you actually plot them, they look completely different. In the first dataset, the points are nicely aligned along a straight line, a clear linear relationship. In the second one, there's still a strong correlation, but one outlier pulls the line away from the main cluster. The third dataset shows a nonlinear relationship. The data follows a curve rather than a straight line. And the fourth one has just a single outlier that creates the illusion of correlation where there really isn't one. The key takeaway is this: statistics alone can be misleading. Before trusting numbers like the correlation coefficient, it's always worth visualizing your data to see the real relationships behind the summary statistics. Of course, we can't always visualize our data, especially when we're dealing with high-dimensional datasets that have dozens or even hundreds of features. In those cases, it's impossible to see all relationships directly on a plot. But Anscombe's quartet reminds us of an important principle. Even when visualization isn't feasible, we should still look for ways to explore our data, for example, by checking pairwise correlations. The main point is, never rely only on summary statistics. Always try to understand the structure of your data in different ways. Another important aspect to keep in mind: correlation is not causation. In other words, even if two variables change together, it doesn't mean that one of them actually causes the other to change. Here we have a funny but classic example. There's an almost perfect correlation, about 0.99, between ice cream sales and the number of drownings. At the first glance, it looks like one might cause the other, but obviously that's not the case. What's really going on is that both depend on a third factor, the weather. When it's hot, people buy more ice cream and they also go swimming more often, which unfortunately leads to more accidents. So the takeaway is simple: even a very high correlation doesn't prove any causal link. Always ask yourself whether there might be a hidden variable influencing both. Let's see how to work with near duplicates, for example features, and linear correlation in Python. We created a dataset that contains a feature which is a near duplicate of another, income. Let's build a matrix of pairwise correlations between all feature pairs. Notice that this matrix is symmetric along the main diagonal. The upper part completely mirrors the lower one, because they represent the same feature pairs. On the main diagonal, we always have once. A feature is perfectly correlated with itself. We can see that the feature dup feature correlates with income almost perfectly, up to 2 decimal places. Therefore, one of them can be removed with virtually no loss of information. We can find all features whose correlation with any of the preceding features in the dataset exceeds a certain threshold, 0.99 in this example, and then remove those features from the dataset. We should keep in mind that duplicates are not always something we need to remove. Now let's look at a few cases where duplicates can actually make sense or even be useful. Natural duplicates can appear naturally in the data and may carry meaningful information. For example, in transactions, repeated purchases can reflect genuine customer behavior. In time series, repeated measurements might show stability or consistency of a process. In text corpora, duplicate documents can indicate popularity or how widely a text has been distributed. And in anomaly detection, duplicates can help highlight unusual cases. The outliers stand out because the rest of the data repeats. We can also have intentional duplicates, added on purpose. For instance, we might use them for class balancing, when we oversample minority classes to make training data more balanced. Or for data augmentation, where we repeat some samples with slight variations to make the model more robust. And finally, sometimes duplicates are used for weighting, giving more importance to certain observations that matter more for the task. Let's move on to the next topic: handling missing values. Missing values are data points where no value was recorded for a particular sample or feature, which means our dataset ends up with incomplete information. And again, we need to take a closer look at why our data isn't perfect. Where did those missing values come from? There are a few simple ways to handle missing values. For example, if the amount of missing data is just a few % of the whole dataset, you can simply remove the rows with missing entries, or even the entire columns. But you need to think carefully about whether you are ready to lose the other information contained in those rows or columns. Another way is to fill in the missing entries in the dataset with some values calculated from the existing data, for example, by using the mean. Instead of the mean, we can use the median or the most frequent value. Let's see how to do this in Python. We'll create a dataset with a missing value. The isNA function allows us to detect missing values. By summing up all the true values returned by isNA, we can see the total number of missing cells. With the dropNA function, we can remove rows that contain missing values. And by passing the parameter axis equal to 1 to the function, we can remove the columns that have missing values. Here we first create a copy of the data frame and then fill in the missing values with the mean using the fillNA function. There are other approaches as well. For example, predicting missing values using machine learning methods. You can check out the imputation of missing values section in the scikit-learn documentation. And now let's move on to the next topic: detecting and removing outliers in the data. An outlier is a data point that differs significantly from other observations in our dataset. It may represent variability in the data, errors, or rare events, and can potentially distort statistical analysis and model training. But what significantly means depends a lot on the context and may not always be obvious. For example, in this dataset, we can see two potential outliers. However, while an age of 110 years most likely indicates an error, even though it's theoretically possible, an income of $10,000 is quite reasonable. So, deciding what exactly counts as an outlier is ultimately up to the analyst. During analysis, it's always helpful to visualize the data distribution, including for detecting outliers. The figure shows a histogram of income distribution. The income scale is divided into several dozen intervals. Each bar represents the number of people whose income falls within that interval. For example, in this interval, there are 10 people with that level of income. In this dataset, $6,000 would look like an outlier. Whether this point is truly an outlier is a question that analyst has to decide. Histograms are useful for looking at the distribution of a single variable. A scatterplot allows us to visualize the joint distribution of two variables. In the figure, we can clearly see two outliers. In any case, it makes sense to take a closer look at those data points. Another type of chart for a single variable is a boxplot. The points show how the data is distributed along the income scale. All the data is divided into 4 equal parts of 25% each. The boundaries of these ranges are called quartiles and are numbered from Q1 to Q3. The value below which 25% of the data fall is called Q1, or the lower quartile. Exactly half of the values are below the median and half are above it. Another name for the median is Q2. Sometimes the mean is also shown as a dot or a dashed line inside the box. Q3, or the upper quartile, is the value below which 75% of the data fall. The difference between Q3 and Q1 is called the interquartile range, or IQR. The box represents the interquartile range and includes 50% of the data. The lines extending from the box, called whiskers, show the minimum and the maximum values that are not considered outliers. A box plot is especially useful for quickly seeing where most of the data is concentrated, how spread out it is, and whether there are any potential outliers or skewness in the distribution. Let's look at an example of data with an outlier. In a box plot, outliers are usually defined as points that lie more than 1.5 interquartile ranges away from the box. It's important to remember that the whiskers show the minimum and the maximum values within that range, not the whole 1.5 IQR itself. So the top whisker points to the highest value still within 1.5 IQRs from the upper quartile, and the bottom whisker points to the lowest value still within 1.5 IQRs from the lower quartile. Using 1.5 IQR is just one common way to define outliers. Depending on your data and your goals, you can set your own rules for what counts as an outlier. We can show a box plot and a histogram for the same data at the same time. Here are the minimum, median, mean, and maximum values of the data. The dots represent outliers, the points that are more than 1.5 interquartile ranges from the upper quartile. You can also take a look at where these points are located on the histogram. So you can use whichever data representation is most convenient for you. In Python, we can detect and remove outliers with just a small piece of code. First, we calculate Q1 and Q3 and find the interquartile range. Then we identify outliers as points that lie outside the range from Q1 minus 1.5 IQR to Q3 plus 1.5 IQR. The drop function removes the detected outliers by the indexes. Now let's move on to the task of removing noisy features. Noisy features are such features in a dataset that contain irrelevant or random information. They don't help the model make accurate predictions and can even harm its performance. It's often hard to tell which features are noisy. To do this properly, it's best to use feature selection methods, but that's a big topic on its own. In the simplest case, you can look at the correlation between all the features and the target variable. Let's take a look at our usual long dataset, to which we have added a new feature called average daily steps. We calculate the correlation of all features with the target variable, sort the correlation values in descending order of their absolute values, and remove the target itself if we don't need to display its correlation with itself. We can see that the correlation between the target variable and the average number of steps is very low. A feature with such a low correlation can be removed, since it's unlikely that the number of steps per day affects the loan amount. We can do this using the drop function by specifying the columns to remove. However, in general, you shouldn't rush to remove a feature just because the correlation is low. First, the relationship between a feature and the target variable may be nonlinear, while Pearson's correlation only captures linear relationships. Second, a feature with low linear correlation can sometimes still be useful when combined with other features. That's why it's better to use feature selection methods to determine the importance of features. And now we move on to the topic of feature encoding. But first, let's take a look at different types of features. Boolean features have only two values, true, false, or 0, 1. For example, gender, the fact of owning property, or the decision to issue a loan. Categorical features represent categories or groups. They are divided into two types: nominal, which have no natural order, for example, profession or loan purpose, and ordinal, which have a meaningful order, for example, education level. Numerical features represent quantitative values. They are also divided into two types: continuous, which can take any real number, for example, income or flat size, and discrete, which can take only specific separate values, for example, age or number of children. Text features contain unstructured text data such as reviews and comments. And finally, date and time features store time-related information such as birth date. So far, we have been working with numerical features. Now we will take a closer look at encoding Boolean and categorical features. Representing text is a separate large area that belongs to natural language processing field. Date and time features are a rather specific topic related to time series analysis, which is also a large separate field of data analysis. So let's look at how binary features are encoded. Many machine learning models can work only with numerical features. So if a binary feature is already represented as 0 and 1, it can be left as is. For other formats, for example, if the binary feature has values like yes, no, or male, female, it's recommended to convert them to 0 and 1. Using 0 and 1 makes the data easier to process, avoids confusion from text values such as yes and no, and ensures the model interprets binary features correctly. In most cases, it doesn't mathematically matter which value is coded as 1 or 0. However, if one of the values represents the presence of a certain property, it's better to code it as 1 for easier interpretation. For example, if a feature indicates the presence of a disease, it's more convenient to encode it as disease equals to 1 and no disease equals to 0. In that case, a positive coefficient in the model can be directly interpreted as having the disease increases the likelihood of the target event. String binary values can be converted to numbers in Python using the map function, specifying which value should correspond to 0 and which to 1. Let's move on to encoding nominal features, which represent categories or labels without any particular order. For example, the purpose of a loan. A common way to handle such features is one-hot encoding. we convert categorical features into binary vectors, where each category is represented by a separate column with a value of 1 or 0. It's easiest to understand this with an example. Suppose our dataset has a feature for loan purpose, which can take 3 values: vehicle, mortgage, and general. In one hot encoding, we create 3 new binary variables: purpose vehicle, purpose mortgage, and purpose general. A value of 1 in purpose vehicle for Alice means that loan purpose of Alice is vehicle. The term one hot means that across all these new binary variables, each record has exactly one value equal to 1. One hot encoding can be conveniently done using the oneHotEncoder class from the Preprocessing module in the scikit-learn library. Let's add the feature purpose to our dataset. We create an object of the oneHotEncoder class. The optional parameters pass output equals false means that for easier viewing, we want a regular matrix instead of a sparse one. The fitTransform method encodes the purpose feature. As a result, we get a matrix of 3 new binary columns where each row contains exactly a single 1. We can also check the name of the feature we encoded and the automatically generated names of the new features. Then we can convert the binary matrix of new features into a data frame with corresponding column names. Note that we use the indexes from the original data frame. And finally, we combine the original data frame with the new one, dropping the nominal feature purpose. In the resulting dataset, we have 3 new binary features corresponding to the one-hot encoding of the purpose feature. The next task is encoding ordinal features, whose values can be ordered in some way. In this case, we can use ordinal encoding, which converts categorical features with a meaningful order into numeric values. Each category is assigned an integer based on its rank. As an example, let's consider the feature education. We can arrange its values as follows. First comes a high school graduate, then a college graduate, and the highest rank belongs to a bachelor's degree holder. We can also use one-hot encoding for ordinal features, since they are still a type of categorical feature. But if we want the model to recognize the natural order of the categories, we need to apply ordinal encoding. In Python, this can be done using the Ordinal encoder class, also from the Preprocessing module from the scikit-learn library. Let's create a dataset with the feature education. First, we get all the unique values of the education feature. Then we define the desired order of categories. We create an ordinal encoder object specifying the list of categories. The fitTransform function converts the categories into numbers. If we are not satisfied with the category numbering in ordinal encoder, we can define our own numbering and apply it using the map function. Let's move on to the next very important topic in machine learning, polynomial features. Let's first introduce a few definitions. Feature engineering is the broad process of creating, transforming, and selecting features to improve model performance. For example, we can create a new feature age based on an existing feature date of birth. This is a special case of feature engineering called feature space expansion, where we generate new features by mathematical transformations of existing ones. One of the most common methods of feature space expansion is the use of polynomial features. The purpose is to enable linear models to capture non-linear relationships without leaving the linear framework. We can think of feature space expansion as a stage of data preprocessing. Let's start with an illustrative example. Suppose we have the following dataset. Let's plot target, in our case loan amount, against income. On the chart, we can clearly see a non-linear, specifically quadratic, relationship. It looks like target depends on income quadratically. So let's introduce a new feature by simply squaring income. We have created a new feature called income squared. For example, if we square 1000, we get 1 million. If we square 2000, we get 4 million, and so on. Now let's plot target against this new feature. We can see that the relationship has become more linear. Let's show that with the new feature, a linear model can make more accurate predictions. First, we will build a linear model using the original feature income. We can see that the model makes quite large errors. Some points deviate significantly from the line. And the mean squared error is greater than 500 million. Now let's build the same kind of linear model using the new feature, treating income squared simply as an ordinary feature, not as the square of an existing one. Otherwise, we would mess up the math behind linear regression training. We can see that the model now makes much more accurate predictions, and the mean squared error has become lower. Here both plots are shown together. Each plot displays a linear model, but on the left it is in the income feature space, and on the right it's in the income squared feature space. If we plot the second model, the one that depends on the income squared feature, in the income feature space, the model will take the shape of a parabola, that is, a quadratic curve. So, by introducing a new quadratic feature based on an existing one and building a linear model in the space of this new feature, we are in fact constructing a non-linear model in the original feature space. This approach makes our models more powerful while keeping the mathematics of linear training unchanged. We simply add new nonlinear features. However, this increase in model power comes with a trade-off, a higher risk of overfitting, one of the main challenges in machine learning that we will explore in the next lecture. We can use both features at the same time, income and income squared. In this case, we can treat income squared as a second feature and build a linear regression model in the standard way, but now with two features. Let's denote income as x1 and income squared as x2. Then the linear regression equation will have the following form. And if we go back to the original notation, it will look like this. The mean squared error for the models with both features will be even smaller than for the models that use income or income squared separately. So in the space with two features, one original x1 and one new x2, our model is linear. But in the original space with only the income feature, the same model appears quadratic. It's the same model. The only difference is the feature space we choose to represent it in, either with one feature, income, or with two features, x1 and x2. The model in the feature space of income and income squared will take the shape of a plane, since it's a linear model. But if we return to the original space with a single variable, income, and plot our model there, it will take the shape of a parabola. The equation remains exactly the same in the both feature spaces. Now let's try to generalize this idea and write down in mathematical form how polynomial features are introduced. Let's say our original features are x1, x2, and so on up to xd. For a polynomial degree of 2, the transformed feature space will include all original features, x1, x2, and so on up to xd, all squared terms, x1 squared, x2 squared, and so on up to xd squared, all pairwise interactions, x1 times x2, x1 times x3, and so on up to xd minus 1 times xd, and the bias term, which is simply 1. That's the degree 0 term. For example, if we have three features, x1, x2, and x3, then the transformed feature space will look like this. The bias term, 1. The original features, the squared features, and the interaction terms, for a total of 10 terms. Basically, new variables appear. Let's denote them as z. So we move from a 4-dimensional space, 3 features plus the target variable, to a 10-dimensional space, 9 new features plus the target variable. Notice that in the new feature matrix, the column of ones that we needed earlier for building linear regression now appears automatically. We don't need to add it manually anymore. If we want to use third-degree polynomials, that is when p equals 3, the terms will look like this. All original features, all squared terms, all cubic terms, all pairwise interactions, all third-order interaction terms, and the bias term, 1. So if we start with 3 original features, the number of features in the transformed space will be 20. We can calculate the total number of polynomial terms. Let d be the number of original features, p be the degree of the polynomial. Then the total number of polynomial terms is given by the formula n equals d plus p choose p. That's the binomial coefficient, which represents the number of ways to choose p elements from a total of d plus p elements. This binomial coefficient can be computed as d plus p factorial divided by d factorial times p factorial. For example, if d equals 3 and p equals 2, then n equals 3 plus 2 choose 2 which is 3 plus 2 factorial over 3 factorial times 2 factorial. That's 120 divided by 12, which equals 10. If d equals 3 and p equals 3, then the total number of combinations calculated using the same formula is 20. Note that the new features don't have to be polynomial. We can also add logarithmic, exponential, trigonometric, and other types of nonlinear features. Let's now see how to generate polynomial features in Python. First, as usual, we define our dataset with the features income, age, and gender. Then we will import the polynomial features class from the preprocessing module. We will also use np setPrint options. It just tells NumPy not to show numbers in scientific notation. Let x be the income column. We will create the poly object of the polynomial features class with the polynomial degree set to 2. Then we apply poly to x. As a result, we will get a matrix with 3 features: a column of ones, the 0-degree term, the original feature, 1st-degree term, and the squared feature, 2nd-degree term. We can also check the attributes of the poly object: the name of the input feature, the number of new features, and the polynomial degree for each new feature. Since in linear regression from scikit-learn the column of ones is added by default, this is controlled by the parameter fitIntercept. We need to set include bias to false in polynomial features. In this case, the column of ones, that is the 0-degree polynomial term, will not be added. If we now apply polynomial features with degree 2 to all 3 features of our dataset, we will get a matrix like this. The number of features will be 9, not 10, because we removed the column of ones. Here we can see the degree of each original feature in every new feature. The first 3 positions contain the original features. In the 4th position, we have the square of the first feature. For Alice, that's 1000 squared, which equals 1 million. In the 5th position, we have the product of the first and second features. For Alice, that's 1000 times 20, which equals 20,000, and so on. We can generate polynomial features of the 3rd degree. In this case, the number of new features will be 19. Remember, the column of ones is not included. We can easily use polynomial features in linear regression, as shown in this example. Here we first generate the polynomial features and then use them to build a linear regression model, which in this case is called polynomial regression. Note that for making predictions, we must also use the new features, not the original ones. The mean squared error in this case is 0, meaning the model perfectly fits the dataset using the polynomial features. Polynomial features are a very powerful approach that allows us to turn a linear machine learning method into a nonlinear one. Let's look at examples of polynomial regression with different polynomial degrees for this dataset. First, we build a first-degree polynomial regression. That's just an ordinary linear regression. Here we can see the regression equation, the relationship between loan amount and income, and the MSE. Then we built a second-degree polynomial regression. Here's its equation. On the plot we can see a parabola, and the MSE has become smaller. In the third-degree polynomial regression, a cubic term appears, and the MSE decreases even further. And the fourth-degree polynomial regression fits all the points perfectly. So the MSE equals 0. It turns out that when the polynomial degree is equal to the number of data points minus 1, we can always fit the data perfectly and get a 0 MSE. We can get an intuitive sense of this using the example of a parabola, which is a second-degree polynomial. A parabola can be drawn through any 3 points, meaning that the polynomial degree is 1 less than the number of points. If we think of x and x squared as separate features, we can imagine a 3-dimensional space, 2 features plus the target variable y. In this space, a linear model takes the form of a plane. And you might remember the well-known fact that a plane can always be drawn through any 3 points in 3-dimensional space. You can try different examples yourself using the interactive polynomial regression demo. It's important to emphasize that even though by choosing a sufficiently high polynomial degree we can always get MSE equal to 0, this approach is not recommended. It's a direct path to overfitting, when a model fits the training data perfectly, but performs poorly on new, unseen data. Let's move on to the last topic in our lecture, feature scaling. First, let's talk about the motivation, why we actually need to apply feature scaling. Datasets often include features of different nature and on very different scales, for example, income and age. But machine learning models only see the numbers, not the meaning. So large numbers tend to have a much bigger impact than small ones. In this dataset, income will be much more important for the model than age. Let's illustrate this difference with an example. We plot 2 bank clients on the chart, Alice and Bob. Alice is 20 years old and earns $1,000, while Bob is 30 years old and earns $2,000. Let's calculate the Euclidean distance between 2 points, Alice and Bob. To do this, we subtract Alice's income from Bob's income and square the result. Then subtract Alice's age from Bob's age and square that as well. Next, we add 2 squared values and take the square root. We get a distance equal to 1000.05. On the plot, we have shown this distance using axes with different scales. So it may look as if income and age contribute about equally. But that's not true. The main contribution comes from income, while the effect of age is almost negligible. If their ages were the same, the distance would change by only about 0.05. The difference in contribution is clearly visible on a plot with equal axis scales. The distance is almost entirely determined by income. Many machine learning models will take this scale inequality between features into account, which can lead to inaccurate predictions. To reduce the negative effect of having features on different scales, we apply feature scaling. Feature scaling is the process of transforming features so that they are on a comparable scale, making sure that no single feature with large numeric values dominates the learning process. There are two common approaches. Standardization, also called z-score scaling, it transforms features so that the mean becomes 0 and the standard deviation becomes 1. Min-max scaling, often called normalization in machine learning, it rescales the data to a fixed range from 0 to 1. And an important note, in scikit-learn, the term normalizer means vector normalization, not min-max scaling. Let's start with standardization or z-score scaling. This is the process of transforming features so that they have a 0 mean and a unit variance, that is, the standard deviation equals 1. To achieve this, we subtract the feature mean mu from each value x. This way we get a 0 mean, and divide by the standard deviation sigma, so we will have a standard deviation of 1. Let's recall that the feature mean is the average value of the feature across all n samples. The standard deviation measures how spread out the feature values are around the mean. It's the square root of the average square deviation from the mean. We've already seen the standard deviation earlier when we talked about linear correlation. The variance is simply the square of the standard deviation. It shows how much the values vary from the mean on average. Let's take a look at these concepts on a graph. Here we have two distributions of the same size, 200 points, both with the same mean of 50, shown by the dashed line, but with different standard deviations. For the blue points, the standard deviation is 5. They are tightly concentrated around the mean, which leads to taller density bars, meaning a larger share of points within each interval. For the orange points, the standard deviation is 15. They are spread out much more and extend farther from the mean than the blue ones. That's exactly what the standard deviation shows us. How far the values tend to fall from the average. Let's calculate the mean and the standard deviation using a simple example. According to the formula, the mean age is 35 and the mean income is 2,960. The standard deviation calculated by the formula is 10 years for age and 1,416 for income. Now let's apply the standardization formula and get the standardized feature values. For example, Alice's standardized age is minus 1.5. This means her age is 1.5 standard deviations below the average age of the clients. Using the formula, we obtained standardized features, income STD and age STD. Notice that the mean for both features has become 0, and the standard deviation is 1. So the features now share the same scale. Note that after standardization, we don't obtain a normal distribution if the feature was not normally distributed originally, and we usually don't standardize the target variable. Let's now see how this works in Python. First, we define our dataset. We import the StandardScaler class from the Preprocessing module in scikit-learn. Then we define the numerical columns we want to standardize. Next, we create new Standardized features. Notice that the scalar object stores the variance, not the standard deviation. Let's now show how standard scaling is integrated into the data processing workflow. Here we use the pipeline class from the scikit-learn module of the same name, which helps organize a sequence of data analysis steps. We will create the following pipeline. First, we perform standard scaling. Then, based on the standardized features, we generate polynomial features. And finally, we build a linear regression model. We run our pipeline and get the predictions. In the variable feature names, we have the names of the polynomial features. We also print out the coefficients of the polynomial regression. Now let's move on to another feature scaling method, MinMaxScaling, which is the process of rescaling features to a fixed range, usually from 0 to 1. To do this, we subtract the minimum value of the feature from each value x and divide by the range max minus min. As a result, if x equals the minimum, the scaled value becomes 0. If x equals the maximum, the scaled value becomes 1. All other values fall somewhere between 0 and 1. Let's demonstrate min-max scaling with an example. Alice's normalized age turns out to be 0 because it matches the minimum age in the dataset. All the other ages fall within the range from 0 to 1, with the maximum age equals to 1. The same happens with income. As a result, both features now share the same range, exactly what we wanted to achieve. In Python, it looks like this. First, we define our dataset. We import the MinMaxScaler class from Preprocessing module and perform feature normalization in the same way as we did with StandardScaler. Let's visualize the results of both feature scaling methods. The blue points on the plot represent the original data with two features, feature 1 and feature 2. We want to scale the data across both features. The result of StandardScaler is shown by the orange points. You can see that the mean of both features has become 0. Most of the points now fall within the range from -3 to +3. This follows from the well-known 3 sigma rule, which states that for a normal distribution, about 99.7% of the data lies within 3 standard deviations from the mean. The result of MinMaxScaler is shown by the green points. All of them lie strictly within a square of side 1, with coordinates ranging from 0 to 1. As a general rule, if you are not sure which method to choose, start with StandardScaler. It works well in most cases and is the default choice for many models. Let's now take a look at how standardization affects the results of linear regression. When we apply linear regression to the raw features and to the standardized ones, the MSE remains exactly the same. This happens because scaling is just a linear transformation, and the regression model compensates for it. What changes are the coefficients. With raw features, they are tied to the original measurement units, dollars for income, years for age, so the magnitudes reflects the scale of each feature rather than its real importance. After scaling, the coefficients are expressed in standard deviations, which makes them directly comparable and shows the relative influence of the features more clearly. For example, in our dataset with the raw data, it looks as if age has a much stronger influence on the result than income, 512.2 versus 17.7. However, this simply reflects the different scales of the features, and such coefficients cannot be compared directly. After standardization, the coefficients become comparable, and it becomes clear that income has a much stronger impact on the result, approximately 25,000 and 5,000. Thus, even in ordinary linear regression, scaling helps us interpret the model. While scaling is not strictly necessary for ordinary linear regression, it becomes crucial when we add regularization. We will talk about it in the next lecture. Or use models that are sensitive to the scale of the features, such as k-nearest neighbors, support vector machines, or neural networks. We are now moving on to the conclusion. So, this is how all the steps of data preprocessing come together. We start with collecting the data, then clear it, fixing duplicates, missing values, and outliers. After that, we remove noisy or irrelevant features and transform the useful ones through encoding or feature engineering. Then we scale the data to make sure all features are comparable. And finally, we get a clean, ready-to-use dataset for model training and testing. In conclusion, we can say that data preprocessing is a really important step. It ensures that the data we feed into a machine learning model is clean and reliable. In this lecture, we looked at several key preprocessing operations: duplicate detection, handling missing values, outlier removal, noise reduction, encoding, polynomial feature expansion, and scaling. We can think about preprocessing on three different levels. At the mathematical level, using formulas and metrics. At the graphical level, through plots, boxplots, and histograms. And at the programming level, using tools like pandas and scikit-learn. When we prepare our feature metrics carefully, our models become more accurate, stable, and easier to interpret.